بسم الله الرحمن الرحیم ولا حول ولا قوة الا بالله العظیم حسبنا الله ونعم الوکیل نعم المولا و نعم النصير. Last time we talked about multivariable control of serial robotic manipulator, and the main important method for this was just to give a short review. Was the IDC controller or the computer torque method, which is formalized here by this block diagram and this equation. As you see in the IDC controller, we have two parts, inner loop controller and outer loop controller. The inner loop controller, which we call it feedback linearization part, handles the nonlinear dynamics of the system and is trying to cancel that based on the model of the system. So TFL include all the model parameter excluding the M, which M comes in the first part. The first part is a PD controller plus acceleration term that we have for the desired trajectory. So we never measure the acceleration term, we never feedback the true acceleration term. And in this structure, we usually consider Q double dot D in the structure as it comes here. So we have a PD controller plus that. Of course, the PD controller can be strengthened with PID or with some other approaches. And the resulting closed loop formulation, if we consider this structure, will be a very nice and linear second order system. Of course, multivariable, everything is vector based, but multivariable. And that's why by this means we can have very suitable performance out of the system. What we can consider here now, the problem of IDC controller is usually the model-based structure of it. And since the model of the system is not quite accurately known, we shall go to some sort of strengthening the robustness of the controller, and we can come to the final picture of our session, which includes the robust and adaptive controller. So we know that we noticed that complete torque method is a model-based controller, and model-based controller is very actively related to the model of the system. And we know that in practice we don't have the model of the system. Considering that we don't know the model of the system, there comes many different methods to cope with the nonlinear dynamics. You don't have any video? Seems like there is no problem here. If you have a problem, please go out and come back to the system. It will hopefully be done better. Now, in terms of nonlinearity and uncertainty of the system, we call system uncertainty. And this is the main important issue that I would like to introduce to you as an introductory course in the control problem. Of course, there are many effective courses here based on linear and nonlinear uncertainty structure and controller design. But here, I just define it. Okay, we don't know the model. Doesn't mean that we don't know all the model. We don't know anything about the model. As you know, we have the dynamic formulation, at least we know the structure of the system, the model of the system. And this, but maybe we didn't calibrate the model quite well, and we don't know exact parameters like mass parameters, especially the moment of inertia parameters, the length of the length, the kinematic parameters, the dynamic parameters. If we assume that the structure of the system, the model, is well developed, and we have quite effectively derived the model of the system, and only the parameters of the system, of the model, is not well known, this comes into one category of non-linear uncertain system that we call the system with structured uncertainty. The uncertainty or the model error is in a structure form. The structure form means that we know the model, but we don't know the parameters. It could be also called parametric uncertainty, which is basically the way that we know how it is going on. As I mentioned, this has a long story, and how to determine that is effective method for that. But we don't want to go in depth of all the details. I will refer to robust control techniques for your further use, and we just have a structured or parametric uncertainty, and this might come because of non-calibrated robot kinematics or dynamics. In kinematics, we have some problem with Jacobian. The Jacobian is based on the length, on the angles, on the structure of the robot. And in dynamics, we don't know the exact mass of the system, or the mass of the, or the center of mass, or the moment of inertia. Just to consider that in an example, consider that you know exactly the robot and all the details, but it is used for a pick and place, and it is picking a load, a payload. With that payload could be variable. It could be 1 kilogram or maybe 5 kilograms. So considering that we are using a very well calibrated robot for a unknown payload, which is usually quite possible in practice, this brings some uncertainty to the system. This mass, which is unknown, comes as a parametric uncertainty to the system. And if we have the parametric uncertainty, if the structure of model is known, we can well go with adaptive control schemes. Adaptive control schemes use the dynamic model of the system as we had before. We use the IDC controller. The baseline is the IDC controller, but the only thing is we get the feedback, and from the feedback of the system, we tune the model parameters, or we adapt the model parameters. It should be in such a way that we can have better performance, or at least steady state error equal to 0. Especially we notice that the gravity terms are very important. You notice that in partial feedback linearization, that the gravity terms are very important. And if we don't know them, but we can somehow identify them or find them through experiment, through online experiment of the system, through online motion of the system, then it is perfect to adapt the model, to change the model during the controller implementation, and then find suitable performance. Of course, adaptation has also some difficulties, and we should take care of stability of the system. If we are not converging to the true variables, and there are diverging approaches in the adaptation laws, then we come into difficult task. Of course, adaptive control is it has a very large range of development, and we just consider some model-based or model reference adaptive control schemes here in this course. But this is not the whole story. Maybe this is the simplest form of uncertainty. The real uncertainty that comes into the model is usually not parametric. Of course, the parametric is available. We have some more than parametric uncertainty in the system. Consider that you're neglecting the friction in the model. Then there is not parametric uncertainty. There is a real model, there is a real physical property in the system that you are not considering in the model. You have unmodeled dynamics. We call it unmodeled dynamics. Or your robot has some flexibility. You have harmonic drive used in the system. There are some flexibility in the joints. And as we usually model the system, we don't use that flexibility because it becomes problem or very difficulty in terms of the model. Deriving the model and calibrating it, not only deriving, but calibration of the model is finding that the true variables are different. Or as we discussed before, we have a nonlinear model with C, with G, everything, and we just did some simple linear identification of the system, and we just used the linear part of the model. This is again another example of having unmodeled dynamics. There are some things within the system which we intentionally neglected, or we don't have the time to get that information quite well, or it is something that we didn't see at all and do exist in the true system. Just to make it a bit more easier to understand, if you consider simple resistance for the electrical system that you have, or electrical network that you have, a simple resistance is usually modeled by V is equal to Ri. A simple resistance with R represent the relation between the current and the voltage. And this is usually true. Parametric uncertainty means that we don't have the exact value of the resistance. It could be 1 kilo ohm, but you know that every resistance has a 10% parametric problem because they are mass produced and we don't know exactly that. But it could be measured quite accurately if we have time. The parametric uncertainty can be diminished in this way. But this simple resistance, if you go back to your electronic courses, you know that if we apply AC current to it and we increase the frequency of the AC current, if you have a DC current, it is quite well, the model is well related to the voltage to the current. But if it is AC, and then we have high frequency voltage applied to this current, then this simple resistance shows some inductive properties from itself. And if you increase the frequency, this induction parameter, which might be very small, becomes more visible. And you can see that this is not a simple resistant, it is inductive and a resistant part of it. This happens for everything, let's say from mechanical property. if suppose that you have a link of a robot, if you move it quite slow, it could be considered as a rigid body. But if you increase the frequency, this link could provide some flexibility to it. And if you increase the frequency, like what happened in a resistant, in this mechanical structure, you brought to the picture some flexibility, some KX, some spring damper property to the system. And you cannot avoid that, because we cannot system. We are engineers, and we just use some simple cases, some simpler model for the system. Now, if considering all this effect, so we have some robustness here in the system. Since that for one little time I lost the internet, but I'm sure, I'm not sure if you are having my voice and my picture, my video. It's fine, Mohammed Mahdi? Okay. You don't have your voice quite clear. Okay. So what we will do in robust controller or in adaptive controller, in both cases, what we consider is not only to consider the model of the system, consider the difference between the true model and the model that you have considered. And we consider this difference as an uncertainty. And we encapsulate it on unconscious. We don't say we model the uncertainty. Because if it was being modeled, then it wasn't the model, the true model of the system. We encapsulate it. Encapsulation of uncertainty means that we just found the bounds, how big, how large this uncertainty can be. And we consider the model of the system, the nominal model of the system, and the bound of the uncertainty. And by using both of these information, we can define or design many, many effective robust controller. We call robust. This is adjective to the property of the system. It means that for example, we are having robust stability. We say that the stability of the system is not only good for the model of the system, for the nominal model, and it is not good just on the paper, but it is good for the model which is perturbed by this uncertainty. So it is much more industrial, much more implementable in the system. Or we have robust performance, for example. Consider that you would like not to have an overshoot for the system. You will see that there is no overshoot for the model of the system, but when you implement it in the practice, there is some overshoot. This is not robust performance, because the difference between the model and the reality will provide some difficulty in the output of the system. We will discuss adaptive control, a very simple adaptive control. Of course, only one way, just to provide you with that. And a simple robust control here. Of course, there are so many adaptive schemes, more than 400 schemes, and very, very different robust control schemes available. But I just want to provide you with the picture how you can come into your mind. If you have the robust and adaptive control in general, there is always possible to combine that. If there is some parametric uncertainty and some robust, some unstructured uncertainty, you have both of them. You can use the power of both of them. Of course, the controller becomes much more complicated. And it is not really necessarily required in practice. But if you would like to have very, very precise controller, what we have done on hard disk drive controllers in practice, then you would like to have very accurate controller, you might combine these two methods and to have robust adaptive controller or adaptive robust controller. In robust adaptive controller, you have an adaptive controller. You design the controller on an adaptive case, and then you robustify it. You add a term to robustify the adaptive controller against unstructured uncertainty. And the same thing for adaptive robust. You have a robust controller which is enforced by adaptive schemes, so we can consider these two together. We don't talk it in the introductory course, but you can find them in practice. And also in robust control, which is mostly, I can say, if we compare adaptive control to robust control, in true implementation, we saw that most implementation techniques goes to robust techniques, and they are more reliable because of the insurance of the stability of the closed-loop stability of the system. And if we consider the robust control, as you see the last part, there is also one other way to use the robust. We can, instead of having a PD controller, which is a linear controller, a simple and linear controller, we can have a robust linear controller. A robust linear controller comes into the picture of H-infinity controller or new synthesis controller. And they are based on frequency domain approach. They are very, very effective. Of course, they need quite a lot of mathematical knowledge about the system, but they are very effective, and I have used that in many, many robotic applications that are apparent in our papers that are published on real robotic manipulation. So this is basically using an H-infinity controller instead of a PI or PID controller. And the main difference between linear robust and non-linear robust is how you model or how you encapsulate the uncertainty. If you encapsulate the uncertainty in a linear framework, you are in a frequency domain, you use the Nyquist criteria and you find the knowledge of the frequency domain to find the uncertainty, to encapsulate the uncertainty, then you can go with the H-infinity controller design to the system. And on the other part, if you what we have usually in robotic manipulation, if you have a nonlinear and multivariable model for the system, then you can go. Maybe it is difficult to go to the linear controller, linear H-infinity controller design. This is possible, but it is more difficult. You can go directly to the nonlinear, robust Lyapunov-based controller design, which we will talk about this in the next slide. So the family of sliding mode controller, which is a very, very large area of research, is developed, and we can say it is interesting to see that the first sliding mode controller which has been applied in robotic application. So the robotic and nonlinear control comes very close to each other in this area. The robotic is a very good application of implementing the theoretical developed robust schemes here. I stood here a while because it is important first to know what we are doing and then go through the rest of the case. Is there any question up to here? So we start with robust control and we end with adaptive control schemes for this case. And as I mentioned, we will go very, very slowly, one by one, to understand the concept and to find how we can go through that. So the first thing is to encapsulate the uncertainty. If you would like to do some robust controller, we call it robust inverse dynamic. It says we are using the inverse dynamic or the computed torque method as the basis, and we are just robustifying that. We are just adding something to it. You will see that. Denote the uncertainty or error by tilde. By tilde command or by tilde notation. When we have a tilde, it means that we have the nominal value minus the true value. The true value has nothing on it. The hat, as we discussed before, was the calibrated model or something that we have done to find the final value. And the error between these two is given by tilde. For example, M tilde or ME tilde, or the effective mass metric, is the nominal values that we have obtained from the true value. And you know that, and notice that. You don't know the true value. Because if you know the true value, then you don't need to describe any uncertainty. What you know and what you're using in the controller is only the nominal value of that, the hat value. And we don't know the exact value of M hat, but we can find some bound. We know that, for example, the M minus ME has 10% error, if we consider it very simple. So this means that we have 10% uncertainty remaining in the system, or maybe 100%. If we have 100% uncertainty, this means that the system is quite uncertain, and it is quite difficult to design. And we go with the same thing with the BE, the viscous friction terms, the C terms, the Christoffel matrix, the G terms, which is the most significant, important part, as you remember, the gravity terms, everything we consider the tilde as the error or the uncertainty that we have here. With the same notation, we consider also for the trajectories that we are using, we consider Q tilde is equal Q minus Q desired. The Q desired, consider that this is the true value that you would like to get, like ME, which is the true value, and what you are there is Q minus Q desired. Because in nonlinear control, we consider usually the tilde variable, although in linear control we use the error. The error is the different the value that you have it, you can measure it, the value that is available there minus the desired value here. And this could be also for Q dot or any other. If you have disturbance, if you have anything else, you have the same idea. So consider that in this way. And by nominal, by designing the IDC control, we just use the M hat, C hat, but we consider this difference in the picture. We bring this different in the picture. So design the IDC by nominal values. We have beta hat, but we add a robustifying term to the controller, but robustify the outer loop controller AR as I discussed it before, you remember at the beginning, we have a Q and tau FL. We consider everything based on M hat, and we don't consider that M hat is equal to M. We add something to this, a Q, to make it robustify. We call it AR. AR is the robustifying term of a Q. So you need to know the previous background. I just go back and forth to ease up the issue for you. Now, you look at here, you consider that tau is exactly like before. You have the feedback linearization, everything on the hat variables, but you have the same three terms here, plus another term, we call it delta A. The delta A is added to the controller, to the outer loop controller, to robustify the system, to find the system, to become the system being robust against the unstructured uncertainty, because against the unmodeled dynamics. And if you use this term, this delta comes into the picture. Now you have if you have to derive the closed loop dynamic, we never consider that M is equal to M hat. We have the M error, M tilde, B tilde, we consider that, and we should apply for that. Find delta A such that for the worst case uncertainty, for the worst possible case that we have, we still have the stability and we still have the performance that we require in the system. So if you derive the closed loop dynamics, the closed loop dynamics Q double dot was, in the previous case, Q double dot was equal to QD minus KD Q dot minus KP error minus K plus KP error minus KP Q tilde. Let me go back again. I'm sorry, don't lose your attention. As you see here, we have the error dynamic plus KD error plus KP error. If these are equal, all equal to each other, we have these three terms again here. In this case, we have these three terms. We call it K tilde double dot is equal to K tilde minus KD Q tilde minus KP Q tilde plus something which include all the uncertainties, which include, we call it a nonlinear function eta, which is a function of M tilde, B tilde, C tilde, G tilde, and also it is a function of AR. It is also function of delta A that we are including here. In the previous case, we just simply neglected this and considered that this is too small. And this is true. If M tilde is too small, if M and M hat are very close to each other, if all the parameters are quite well calibrated, this term becomes small. But this is just an assumption. In real implementation, these are not very small, and this could be somehow different. And this ME hat comes from the picture. If you, again, I go back here, this ME hat, as you see, comes into the picture. It was multiplied by this error equal to 0. So we should also include ME hat inverse in the picture of this system. Just write the closed loop dynamic. You have the dynamic equation, you have the torque. Apply it to the system, you come to this picture. And this is basically your ME minus M inverse. And it is very fortunate that the true mass matrix of the system is always positive definite, and we have some inverse. This inverse always exists. We don't have singularities coming in here. Now, we have an eta, which is quite big. All the errors are within that. And if it was not there, it was very simple, but it is there, and we don't know the exact values here. We consider that we know the bound of it. How we can design, if you consider that eta here, and you will bring the AR here to the picture, you have a delta A and eta. Eta is very large, but I just forget about the argument here. I put it here. Substitute eta in the closed-loop dynamic. You can see that the closed-loop dynamic is very similar to the previous case, the second-order case that is quite linear and parametric and vector-based or diagonal. It is somehow multivariable, but since we are using diagonal terms in KB and KB, it would be very simple. But unfortunately, we have an eta here, which comes from all the uncertainties, unknown parameters that we have in here. If you look at this very naively, you say, okay, very good, we have a delta A to just compensate for eta. So if we know eta quite well, we use delta A equal to minus eta to get rid of that. Then we reach to the same previous second order controller that we have in IDC. But this is never possible because we don't know the eta. Eta, we know we can know the bound of it, but we don't know that. If we consider that we know the eta, then we consider uncertainty. If we call uncertainty, it means that we don't know what is exactly the value of that. Let me explain it in a parametric form, an example for you. For example, you have a resistance. You buy a resistance from off market, and then it says that the resistance is 1 kilo ohm plus minus 10%, or plus minus 2%, and plus minus 1%. But it is never exactly 1 kilo ohm. If it is only plus minus 1%, this means that this resistance can be 1.01 kilo ohm or 0.99 kilo ohm. But you don't know if it is 998, it could be 992, it could be 1005, it could be anything. It is not, you don't know exactly what it is, but you know that it is limited within 1%. So it is between 0.99 kilo to 101 kilo. This is a simple parametric uncertainty. For every other cases, you don't know exactly the eta, but you just know the bound of it. What we call here, we consider the norm if it is norm bounded. We consider that we know the bound of eta as the uncertainty encapsulation. So we don't know that. We cannot just simply substitute and get rid of that. We shall use some linear. So now we go with that and start to design the robust controller. The idea is to define delta A, which is a design parameter we add to robustify the controller, to take care of the worst case possible eta. And this worst case possible eta is the maximum uncertainty that we can have. For example, if you have a resistance with 1% error, the error maximum of it is 1%. So we consider 1% error for this parameter and all the other parameters, and consider that we can define a delta to compensate for the worst case eta value. So this is very important, and this is the essence of a robust controller. It is quite different from adaptive. In adaptive, we try to find the true value of that, But in robust, we don't find the true value. We consider it that we know the maximum, the worst case possible, and we just want to get rid of that, the effect of that, by adding a robust controller to this system. To do that, we just go one by one. We consider first the linear state space formulation, and then we add a nonlinear robust controller to it. So we rewrite this equation, which is a second order equation, in terms of state space formulation, which is a first order equation. It is very simple. We just use 0. Q tilde dot is equal to Q double dot tilde, and then Q double dot tilde is equal to this, as you see, KD, KP, eta, and so forth and so on. So you can write an equation like that. It is very similar to a linear equation, but it is not linear. Eta dot is equal to epsilon dot is equal to epsilon. We consider that as epsilon, the error in a vector form and in a state space form. Plus B, if this was a U, a simple U, it was a linear form. But this is not linear. You know that eta has a lot of nonlinear term within it. So this is still a nonlinear dynamics, but written in the state space form. And you consider the linear part and also the nonlinear part. And B is equal 0 I, very simple, because you use the first derivative, the first equation, the derivative of the first equation is the second state space that you have. So to do it, to stabilize the system, we should first stabilize the linear part. The linear part, yes, I will talk about that, Ashkar, in the future. Let me just reach to that point. I will talk about that, Ashkar. So we consider the linear part and also the nonlinear part here. First, examine the linear part. This linear part shall be stable, and this A equation, as you see, it is very simple. If this should be stable, all the eigenvalues of A should be negative in the open left half plane, all be negative, and then we can consider that to be stable. And then we should define delta somehow to accomplish or to get the effect of to compensate for the eta, especially for the stability. This is very important, that the system becomes stable, and furthermore to have very good performance. So we can consider this linear term by its eigenvalues, or we can use the Lyapunov matrix equation for that. And it is much more effective, as we saw in the modern control, that Lyapunov matrix equation, which is ATP plus PA is equal to minus Q. If we can find any positive matrix P that can solve this Lyapunov matrix equation, then the system is always positive. And this is important because we use the P and Q in the rest of the analysis that we use. And this is just, for this case, we should have positive KP and KDs to have positive, even just positive KPs is enough, because it is upper triangular to be positive definite, and or to be basically a stable system. So consider that we have for any positive symmetric definite Q, we have ATP plus PA is equal to minus Q, and then the linear subsystem is stable. But this is not enough. We have to work on the nonlinear part. How we do the nonlinear part? We go with the Lyapunov method, and we design the Lyapunov function based on the error of the system, epsilon transpose P epsilon. P comes from the linear part here, and then we put it here. Consider that we have a positive definite value for the Lyapunov function or the Lyapunov candidate, and then we differentiate it with respect to time or along the trajectory. Differentiation of that becomes epsilon dot plus epsilon P epsilon dot. We have both P's and P. Since P is constant, we have two terms. And then we know that epsilon dot, as you see here, is equal to A epsilon plus B something. So we have ATP plus PA plus something. This something, B times delta plus epsilon, as you see it. We have the P also available here. And these two terms becomes basically the same. We have two terms also coming before that equation. This part, since the linear equation was stable, the linear part of linear subsystem was stable, we can just replace ATP plus PA is equal to minus Q. This is negative definite, but we have another term which is nonlinear, quite heavy, and it could be positive. And this becomes some problem. Even the uncertainty in the model can cause instability in the closed-loop system, which is quite bad and undesired. So, coming to this picture and having the Lyapunov derivative here, there are 100 methods to design delta, you see delta, such that this term becomes negative definite. If this term becomes negative definite, it means that V dot is equal to something negative definite and phi. Even if it is equal to 0, if we can do it equal to 0, again you see, if we know eta and we consider delta is equal to minus eta, then it was done. But we know that this is not possible because we don't know the uncertainty. We call the uncertainty, we don't know the uncertainty. We should take care of this second term to become somehow negative. So how we can do that? For all eta, we consider the worst case scenario. And this is the question of Ashkan. How we find this worst case scenario, this is also very important. I will talk about it a bit here and a bit at the end of the class. Here, if you see, we assume norm-bounded eta. You know, we are somehow encapsulating the uncertainty. The eta was all the nonlinear and uncertain terms. We consider it as we have a bound, an upper bound of the worst case of it. We call it phi rho. Rho is a scalar function. It is a function of the state. This is a function of time. The time comes into the picture, could be coming into the picture if we have some desired trajectory, because we have the errors here, the desired trajectory as you see here, we have QD dot. So time comes into the picture, could come into the picture, and we are just assuming that we don't know the eta, but we know the bound of it. This assumption is much better than considering that there is no eta, or we know exactly what is the eta. This too is not a good assumption. This assumption is much better, but as I mentioned, this is also not very easy. How to find the norm of R? This means that if we go back, if I would like to answer the question of Ashkan, if you go back and see what was eta. Eta was depending on the error of the trajectories, Kp, Kd gains, the closed loop dynamic, the error in the mass matrix, the error in the viscous friction matrix, the error in the Christoffel matrix, the error in the gravity matrix, and so forth and so on. Just for now, consider just the gravity matrix. This is for Ashkan, because I know why he's asking this. It's required in his thesis. Consider only the gravity matrix. So we would like to find the norm of eta just by the gravity, just for a simple case, consider that all the other terms are equal to 0, and we have only the gravity term. How we can find that? The gravity tilde. The gravity tilde means the gravity hat term minus the gravity term. So you know that you have some model for the system, you have the gravity, and you have a true value of that. So you can do some experiments. You can do some experiments. The gravity is the static value, so you can move the robot up and down with different Qs, of course, within the workspace of the system, and experimentally find the difference between what you have considered as the model through the true value. And the gravity can be measured quite well, because if the gravity term is equal to 0, the robot will stay at the position it is there. So you can put some counterbalancing weight and then move it to different approach and get the values of counterbalancing equation, and then you find the difference between G and G hat in the real values. So for how many experiments you do that? As much as you can. So you know that you have compensated for the gravity, but not the whole gravity. There are still something, for example, if the gravity vector norm, the gravity is equal to 100 kilograms, just to make it, you have 99% of it, you have compensated by the 99%. The G hat is 99% right, so you still have 1% error. So the gravity term can be considered, the norm of the gravity term can be considered here as 1 kilogram. And the same thing can happen to the other one, of course, not statistically. The gravity term can be measured statistically, but the other one, the Christoffel term, should be considered just by a dynamic experiment. You have a dynamic model of the system. You have something that you can measure, the torque that you can measure, the current that you have in the motor machine, and you find the difference between these two together, all together, as the gravity term. And if you cannot measure that, of course, if you can measure exactly what it is, then you have the eta quite well. If you cannot measure it, you can just consider some upper bound with some, we call it conservatism. You consider a larger value. It might be only 1 kilogram, but you consider 10 kilogram to make sure that it is within the bound. And this conservatism is not good, but there is no way to do that. Again, this part is the most difficult assumption that we are doing, but it is possible to find that. It is difficult, but it is possible to do that. Are you okay, Ashkar, with the answer here? Are you with us, Ashkar? Oh, Ashkar is just what cannot talk. Are you okay with us, Ashkar? Okay. Now, consider that we have the bound here. We don't have that much time left. I should give the main result here. Okay, if we consider that, and to make it a short notation here, we have 2 epsilon b, something. And we consider all of this as a vector, epsilon transpose p, which is a matrix, b, which is a matrix like this. We consider that as a vector, we call it v, vector v is equal to b transpose p epsilon, b transpose p epsilon. And then if we consider that, we have 2 v transpose delta plus eta here. And we know that eta is bounded from above by the row variable that we have. So here there are so many different methods. I just mentioned one method here, which we call Lyapunov redesign, or design that is given by this structure. We design a controller. We don't just cancel this by that. No. We use a delta A to make this, the effect of this, becoming non-negative. It is always non-positive. It becomes always negative. We consider delta as a negative value. Of course, it should be negating eta times v over norm of v. Rho, which is the value that we have, the upper bound of the uncertainty. V, which is a vector, v is defined here, divided by the norm of v. To explain why this is important, this is very, very important, and it comes from the Jacobian analysis. I cannot give the details here, I'm just giving the result here. But how it is developed in robotic manipulators comes from the Jacobian. It comes from the mapping between the forces that we have and the torques that we require. But to make it a bit familiar, to make you a bit familiar, consider that V was not a vector, it was a scalar. We have only one variable here, not multi-dimensional robot, just one single degree of freedom robot. So we have V divided by the norm of V, V divided by the sine of V. If V is equal to 5 divided by the sine of V. So it gives a gain, a positive gain here always, the V divided by the sine of V. If it is minus 5 divided by the norm of V, which is exactly 5, minus 5 divided by 5, it gives you minus 1, gives you the sine of V. If it is positive 5 divided by the norm of V, which is 5, it is normalized, somehow normalized. Then it gives you the positive value. So it is an on-off controller, or is a sliding mode controller that you might have seen in your previous courses, and on-off.
It's fine now.
So I was talking, it is good to interrupt at this portion because you need to think about it. So if it was scalar, a scalar value divided by its absolute value gives the sine of the value. So it is a relay controller, an on-off controller, a bang-bang controller that we usually use. And this bang-bang controller is multiplied by the rho, the maximum value of the uncertainty. Let me give you another example. This is the physical body of here. Just consider a simple scalar case. So we have a high gain here. Rho is the maximum value of the uncertainty times a negative and positive case. I usually give this example for a robust controller in many classes. A robust controller is like a boxing game. Consider that you are a boxer, but a boxer within a free weight boxing game. You might be 80 kilograms, might be 100 kilograms, but your competitors, because it is free weight, it could be 120 kilograms. It could be quite larger than you. And in a robust controller, you should use your fist, to have positive or negative with the maximum value that you can put in your fuse. So you are 80 kilograms, your competitors is 120 kilograms. So the rho, the value, the difference between these two, the uncertainty that you have is 40 kilograms, about half of your weight. It is 50% uncertainty. So you should be so practicing, so powerful to put your fuse with 50% above your weight power. And what you do, you just use plus, minus, plus, minus. If you don't be hit by your competitor, the most important thing is you go on the competition. On your first fuse, you should put the maximum power in your arm, the maximum with 50% difference in the weight, and you put it there. If you can do it, you can still win the game. But if your competitor is 180 kilograms, you might not have the power to, break him down. This is the way that the robust controller work. You say that what is the value of the uncertainty, the bound of uncertainty? We call it rho. So put a minus rho just by sign, plus or minus, plus or minus. This is for a scalar case. If it is not scalar, if it is a vector, this won't be a sign, a simple sign. It would be a multivariable sign, somehow a multivariable case. Of course, it is quite advanced. Usually in nonlinear control, we start with a single parameter and then go to the vector race. But in robotic, we cannot go with a simple case because you usually have a multi-degree of freedom. We have a multivariable case. Now look at this equation as a vector. Suppose that we have a vector 1, 1, 1, just simple, three value vectors, 1, 1, 1, and divided by the norm of v. The norm of v would be the square root of 3 here, 1, 1, 1, so we have square root of 3 here. But the important thing is, if you have 1, 1, 1 divided by square root of 3, this is somehow normalized. But if you have 1 minus 1, 1, again the norm of it would be square root of 3. It means that the direction that you are applying your torque, 1, 1, 1, means that all the torques in the first three joints should be equal to each other. You have 1 minus 1, 1, but that your system is not all positive. The first one, the last one is positive, the second one is negative. Here the sign come into the picture. A normalized sign, a weighted sign. Exactly this is V divided by the norm of V, a vector divided by the norm of V. And why this is important? This keeps the direction that you are applying to your force. Your torque is a vector, is a linear algebra, and you're keeping this. If you change the direction of that, you never get to the direction that you would like to go. You find what would be your B by P transpose P epsilon. Epsilon is the error that you have, and the error that you have gives you which actuator should be positive, which one should be negative, which one should be large, which one should be small. The direction in the space is fine, and then you normalize it by this vector. And this normalization is required. It has the sign value in it with a very large gain. The gain that we are adding to it is also quite large. Remember the boxer. And then you're applying this to the system. The system, if you see the final, the mathematics is very simple. It makes this vanishing. If you put this here, instead of delta A you put here, so we have the V dot, as you see. We'll just look at the second term here. The second term you have without 2, again 2 is not important because positive. The second term here is V transpose delta plus eta, V transpose delta plus eta. But we have a V transpose multiplied by that. Just in the worst case, if you consider this should be smaller or equal, not equal to each other. If you multiply this to this V transpose, we have V transpose times V divided by the norm of V. This is V squared divided by the V. This becomes the norm of V, exactly equal to norm of V. And we have V transpose to eta. The worst case possible case, this should be, of course, smaller or equal to that, is equal. This is always larger than that. We have V transpose times eta is always smaller than norm of this multiplied by norm of this. This is the Schwarz inequality equation that we have. So this means that rho times V times eta, very nice. So we can consider V coming out, since this is scalar, and this is scalar too, minus rho plus eta, norm of eta. And we know that rho is always greater than norm of eta. So this is always negative, definitely. This is always negative. If we consider multiply, if we consider keeping the direction of the vector V and just dividing it, but it is doing like a magic. This is not magic. This is well known by bang-bang controller. This is well known by sliding mode controller. If you have some knowledge in the area, in different area, and this is one method to do that. You can do from 400 different other methods that can be done. You can just using this equation make it equal. This would be smaller than this. So this term will be cancelled or neglected with respect to this. V dot would be always negative definite. And then you have a stable system. It means that by using the eta term, we have at least considered that for the worst case scenario, you see now how the worst case comes to the picture. For the worst case scenario, you can guarantee the stability of the system. And if you have the stability of the system, you can also have very good performance out of the system. Notice that this is somehow a multivariable sliding mode controller, you can call it. I will call it Lyapunov redesign. This is mostly in the Lyapunov redesign controller case. So what would be the final value? We are almost out of time. Let me just conclude here. We have all the previous cases, the inner loop, the outer loop, everything like the robust computed torque method or the IDC method, but we have only added one robustifying term, delta A, which delta A, as you see here, the delta A, as you see here, is something like that. If the V, of course, V divided by norm of V could not be equal to 0. We require to make a V equal to 0, but we do that asymptotically. V divided by norm of V times the rho, the Keigen. Ashkan asked us how you find the rho. If you don't know rho, make rho very large gain, high gain controller. Of course, you cannot do it very high because you have limit in the actuation. But make it high gain. Put your feast, the most powerful feast that you have, and just hit your competitors, hit your system with the robustifying gain. If v is not equal to 0, we have the robustifying term. And if v is equal to 0, because this is a sign, we consider that is equal to 0. So if you have a positive or a negative, depending on the size, and if v is equal to 0, it would be exactly along 0 variable. And this will cause stability, asymptotic stability of the system. You have 0 steady state error. Although for the worst case nonlinearities and uncertainty that you have in the system, you can have steady state error equal to 0. And by increasing the gain, you can also shape your and don't forget that KB and KB, which was the linear part, are very important. Still, KP and KD can form the transient response, the zeta, the omega n that you would like to have, and you can use the linear controller part to have this going on very well. Is there any problem here? Is there any questions? Is there any problems? I need only to add one more slide here, which is the final case. Of course, it could be discussed more than a week about that, but we don't have that much time. I will try only to give one more slide here. This is very good theoretically, but in practice, this is a discontinuous controller. The discontinuous controller have some problem in practice in implementing. It is a bang-bang controller. And the problem with a high gain, we have a delta discontinuous and high gain. This cause, we call it, it will result into chattering. The chattering, we translated in Farsi to Tawatur Namunazam. Don't say vez or something which is not very familiar with the Tawatur Namunazam. This cause some oscillation at the end effector. The chattering, what is the chattering problem? Say that, okay, consider this equation, it is very quite exponential term which is decaying to the 0, but we have some noise. We know that in robotic manipulator we are usually using encoder to measure the cues. The encoder have some quantization error. You know that in the robotic manipulator we are implementing all the controller in digital case. We are using microcontroller, we are using PLCs, we are using digital controller. And digital controller, that means that we have sampling time. We don't know all the effect, all the variables. We have noise, especially quantization noise, and we have sampling time. What will happen, you will see, although this is decaying to 0 because of the noise and sampling time, enlarge it here, you will see that although it is going to 0, but we see that it is coming positive, negative, positive, negative. And positive, negative, since we are using the sign, and you are using your fist, right, left, you have positive, negative with high gain. So we have some on and off, or some bridging or some oscillating input giving to the system, so the system becomes also oscillating. We call this a chattering phenomenon. And the chattering phenomenon is not very suitable, especially for robotic manipulation. We don't want to have some noise or some oscillation at all in a moving platform or in an end effector. So there are also many ways to rectify this problem. But what we do is usually we continuify that. Instead of having on and off like V divided by V, very close to 0, with a threshold that we consider the threshold epsilon, the small epsilon here, and delta with the rho variable here, we consider that if we are in this threshold, we consider a linear part. Instead of having bang-bang controller, we have also a linear part. We continuify. We make the discontinuous function to a continuous function. You can see this is continuous function. It is not differentiable. Still, we don't have differentiable here, but it is continuous. And then by continuifying this, like what we do in sliding mode controller, we can have a non-oscillatory output. Of course, we reduce the stability, the asymptotic stability to, we call it UUB stability. We have some steady state error because of this continuifying error, but it will result into the case. No, the differentiability is not important here. It should be continuous. But of course, if you can do it very smooth, of course, instead of using a simple linear case, you could use a tangent hyperbolic case. Tangent hyperbolic is quite continuous, differentiable, and it is not that wide. It is quite high, but it is more difficult in practice. But by using usual microcontroller that we can use tangent hyperbolic instead of this. You can even use some fuzzy rules to continuify here. You have some fuzzy membership function, and then just use them. There are so many other methods to use that, and of course, in sliding mode controller, in nonlinear controller design, there are so many different ways to use such a controller to be implemented in real practice. But believe me, this robust IDC is working very, very well. And it is, I don't say that it is used in all the robotic manipulator in industry. No, in most of them, we are just using a robust PID or a PID with tuning gain. But if you need it with, higher accuracy in terms of presence, in the presence of uncertainty, you can use that. We are running out of time. If there is any question, we have time for 2 quick questions. 1 or 2 quick questions. If there is any question, please. Yes, Hussein? We have your some delay. Yes, just talk and talk louder.
Having my voice?
Yes.
Yes. In this case, do we have an advantage concerning time or response time rather than modeling the uncertainty directly or modeling the error?
No, actually, if you would like to go through the robust inverse dynamics, you need to go through the method that I am mentioning. If you don't want to go that way, you can go to the data-driven base method. There are some other ways that you just use the time series of the output. But the stability there is usually not very well verified. The stability analysis is very important. You know that if you are using a robot in a space or somewhere that it cannot be, it is very, very fragile or very important, the stability is becoming important. So there are other methods, of course, data-driven, TDE we call it. You can go to fuzzy, you can go to neural network, you can go to ANFIS, you can go to the different methods, but all of them have some difficulties as well. I recommend, since we are the controller that we defined was based on IDC, I recommend to have two variations of robust and adaptive cases in your issues.
Talking about the advanced.
We don't have your voice. Still, we have your voice. Okay, go ahead again. Repeat your question.
My question is concerning the advantages of this robust ITC.
Mm-hmm.
Since we are not directly modeling the error or estimating the error, my question or my intervention, there is an advantage for this controller concerning time response. Is it true?
Okay. Yeah, I understood now what you mean. This cannot be said in general cases, always. But the robust controller, since you are adding a high gain controller to the system, and if you can increase the gain, the raw gain here, you have very good time responses. You can have very well-defined time responses out of that. If you don't have a limitation on the, much limitation on the controller for that you are working. It is much better than adaptive or other methods, which are quite lean and quite slow. Here, since we are using high fierce, it is quite fast, but the problem might come from the chattering. So you can have, by increasing, you have now three parameters to tune. One is the raw parameter here, and the other one are KP and KD that you had before. You have three parameters now. And you will do that in your project, hopefully, in the final project on the robot that we give you for the surgical robot. You will see that by increasing the gain, you can have very good time response out of the system.
May I add a question for next time?
I didn't again hear you. Can you?
May I add a question or for
Sure.
next time?
No, go ahead.
The bounds or the capabilities of the actuators can give us a vision or a view about the maximum boxing torque or boxing force that I could.
Of course.
We can start from there.
Yeah. Usually, yeah, of course you can see from there. This is also very good intuition. Good to see a practical way of doing that. It is not very easy because but you can start with that. This could be a continuation of Ashkan question. You can start from the dynamics to find the value on the row, the maximum value of row that you require. Hussein is asking from the other way, going from the actuator effort, how big we are and coming to this case. Of course, usually we design a controller with not very overcompensated actuator. If you have a robot with 10 kilogram payload, the motors are somehow 4 to 5 kilowatts. Of course, you can use 10 kilowatts there, then you have a much higher gain over. But it is not, very economical to design such that. But if you have a controller, if you have a robot designed already, you know how much out of the scope you can get, how much payload you can get. You have a robot, now you have a payload which is adding some uncertainty to that. And this is usually the case. Usually, from the over design of the motors, we can find how far we can go with the payload. But this is not the good way to do that. You usually don't want to pay too much for the motors and just to have a boxing, properties that you might not usually be able to use that. But usually 10 to 20% over design is usually the case for the robot. 10 to 20%. Thank you very much, everybody. And our next and last session would be on Tuesday. And if there are some questions, if there are any problems within the course, please give us your question next time, and then we go through the program that we have on the problems and the examples and on the exams. The final exam of yours would be something similar to your midterm exam. You would have about 2-3 hours exam working on some particular cases. They are mostly related on dynamics and control, but not limited to that. So you need to have Jacobian, you need to know David Hartenberg or kinematic to do this part as well. But it is mostly, the questions are mostly concerned with the dynamics and control that we didn't cover in the midterm exam. So I hope that you have enjoyed up to here the classes, and you will be with me for the next and last session of the class in Tuesday. Thank you very much and good day.